Morning. How are you? Ready for the new week? All right, so we talked so far about controller design, observer design, what happens to non-minimal systems, and all of that was for linear systems, linear time invariant systems. Today we will talk about non-linear systems, which is kind of more interesting, but we will not get too far away from actual linear systems. We will do linearization of non-linear systems. So we'll try to bring specific non-linear systems to something very close to linear, in a sense. We will linearize them. And this will work only in very narrow ranges of input signals and of values around particular points that we will call equilibrium points. And equilibrium points you might know from physics what that means, but we'll talk a little bit how we define it in state space, what equilibrium points are. And this is same thing like in physics. But here's the motivation for what we are doing here. Most of the systems that I know of are nonlinear. Actually, all systems that I know of are nonlinear. Okay, I don't know about any really physical linear system. All of them are nonlinear. Many systems could be approximated by linear systems. But this is very similar to what you could say about curves. Okay, you can approximate practically any smooth enough curve with straight line. Will it be a great approximation? Not really. Sometimes, depends, right? We know all of these approximation things. If your curve is changing too much, it's very wiggly, linear approximation will not work very well. But if it is kind of like that, pretty smooth, not changing too much, then straight segment would approximate it pretty well. All right? Same thing happens with the systems and linearity of the systems. If the system behaves well, and I'm not even defining what it means, but it's like smoothly changing, right? It has nonlinearity, but this nonlinearity is not really strong nonlinearity, not like step nonlinearity, right? It's continuous, differentiable, all of this nice property, smooth, right? Then you can approximate it with straight segment, but farther you go from that particular point where you approximated with that straight segment, more likely you get bigger error, right? This is expected from any function. You have any particular function, let's say it looks like that. You want to approximate it as a straight segment here, so you're doing the derivative approximation here. So farther you get from that point, the error typically gets bigger, okay? So this is a problem with all of the linear approximations, which means that for all of the approximations that we will be doing here, it works well close enough to that point. Okay, so around it, the approximation is fine. All right. So most nonlinear systems could be written in state space form like that. And pay attention that this function might be any nonlinear function you want, and this function might be any nonlinear function you want, which is working on state x and input u. Each one of them might be vectors, obviously. Okay, so x is vector and u might be vector if you have multiple inputs. So this could be any function of x and u. The only limitation here in that representation is that x dot is separate. So you kind of took it out. For some systems, it's not really possible. So you can write it only in implicit way, which means x dot is buried somewhere inside the f function. Okay, so you have f function of x dot, x, and u, and maybe higher derivatives of x. All right, so sometimes you cannot really write the differential, nonlinear differential equation that you have as x dot equals something, and whatever that something is. So you cannot extract it out. Let's say if you have, I don't know, some simple example, sine of x dot equals cosine of x dot plus something u square, whatever. So the trigonometric equation, you cannot solve it for x dot, let's say. Okay, so you cannot explicitly write x dot as a function of everything else, because the connection between two sides is non-linearly complicated. But in most cases, for most systems, you actually can write it that way. And then you can do linearization to your system, okay, when you write it that way. So you have x1 dot, x2 dot, x3 dot, all of the x dots equal to some linear or nonlinear functions of x and u. Okay, so it could be practically anything. And y is the same thing, could be x squared plus sine of x plus whatever, right? So it could be any nonlinear function g. Any questions so far? So this is nonlinear state space representation of the systems, which works for most physical systems. Now, we want to define equilibrium points around which we will do that linearization process. We'll convert it into linear system somehow, close enough. So equilibrium points, try to imagine like ball with a ball inside, something like that. This is how in physics you learn about equilibrium points. So if you move that ball like left and right, it will shake inside, the ball will shake inside, and we'll get back to the bottom of the ball, right? So you have something like that. Here you have some ball inside. It will center here somewhere after a while, if you shake it a little bit, okay? Now, you can think about another point where it will not stay at the same point, but when you leave it at that point, it will stay there, okay? So if you invert that same thing, like that, and you put that thing on the top, right? It will stay there. But if you shake it a little bit, it will fall, right? So both of these points are called equilibrium points. But this point is stable equilibrium point, which means if you kind of move it a little bit, it will return to that equilibrium point if you move it close enough. Because if you shake it too much and it flies out, obviously it will not return anywhere, right? So it's good only for particular distances from that equilibrium point. So you have some range of distances for which it will return back to that point. And this is called attraction region from which it's still attracted to that equilibrium point. And then you have other types of points from which no matter how tiny your disturbance is, it will not return to that point anymore. But if you are not disturbing it, it will stay there forever. There's no disturbances. So both are equilibrium points, but this is stable equilibrium point, this is unstable equilibrium point. And for typical nonlinear systems, all of this terminology is local, which means for particular subregion around that point, not too far away. And this is where we will say, oh, the system is close enough to linear in that sense. In both cases, close enough to that equilibrium point. So how we can define that mathematically, equilibrium points in general? So for continuous time systems, we just say that the solution of that function, remember that function is x dot. Practically we're saying that x dot equals to 0. This is equilibrium point. You need to solve equation x dot equals to 0. Why does that make sense? Because what is x dot equals to 0? So x is a function of time, right? X is a trajectory in n-dimensional space. There's some line in n-dimensional space. And I'm saying x dot of t, which means first derivative in time of t, equals to 0 forever. So what does it mean in terms of trajectory?
Independent of.
Independent of what?
It's the system is a constant value.
Yeah, so practically speaking, what does it mean x dot equals to 0? It means x is not changing, it's constant, right? So it stays wherever it is. Okay, so you have particular x. If at that point x dot equals to 0, it is staying the same x all the time, right? You continue to have the same x over and over again in time. So it stays wherever it is. This is what x dot means. Because derivative of x is change in x, right? Derivative is change. So there is no change. X is not changing. In discrete time, how can we define that we do not have change. If you remember, discrete time systems are x of k plus 1 equals a x k plus bu, blah, blah. Okay, this is our system. So we want that the next state, which is x k plus 1, or next state, right, equals to the previous state. So it's not changing. And this is a condition. So x equilibrium of k plus 1 equals previous x equilibrium of k, right? So it will continue forever if this is true, right, for all k. So this is how you define equilibrium point. You define it as f equals to 0 or x dot equals to 0 because this is x dot, right, as we defined here. So this one equals to 0 for that point, so you can solve for x equilibrium and u equilibrium and to find them, like where this equation is actually true. And for discrete time systems, you're solving that equation, which means that in that case, it will be not x dot, but it will be xk plus 1 equals some nonlinear function of whatever. But you're solving that equation to find equilibrium point for discrete time system. Any questions? And again, physically, this just means that the point stays wherever it is at this moment. And we will be linearizing systems only around these points. So all the developments that I will be doing right now in this lecture are related to these equilibrium points. So I will approximate the system around these curvatures somewhere, close enough to equilibrium point. It will not work far away from equilibrium points. Okay, the error will be too huge. You can try. People are trying to do that and to use linear approximation for that type of curve with long line, but well, nothing is promised then. Okay. So here's what we propose to do here. First of all, we can write small change as delta symbol, that type of little delta symbol. And pay attention that delta x is not delta multiplied by x, and this has nothing to do with impulse response, okay? Different delta. That entire symbol delta x means just small change in x, okay? And obviously it is function of time, right? X equilibrium is not a function of time. It's particular point, particular state, which is equilibrium state from which it would not move in any time. So xe is not a function of time, but x in general is a function of time. So what that expression means is small change from the equilibrium point in terms of state, okay? So this is trajectory close enough to that 0 point or whatever the equilibrium point is, all right? This is the meaning of that thing. Same thing I'm defining for y. So it's y equilibrium point, which could be anywhere based on the equations that you solve here. Same equation you have for g. So you find that equilibrium point plus some small change in y, for which we will write the linear system, right? And same thing for u. So you will have that equilibrium u, which you found from the solving the equation on the previous slide, plus minus some delta. Yes.
Is it like plus or minus small delta change, or is it just plus?
Plus or minus. I mean, the delta u or delta y or delta x might be negative.
It can be negative too.
Sure.
Yeah.
It could be positive or negative. It's like small fluctuations around that point. So you close enough, okay? And that's simple just to say that this is small, okay? In calculus, people are using delta and epsilon for defining small things. So you have all these deltas, and I want to put it inside of that system to see how I can develop that further, how I can approximate the system with something linear maybe. Because working with function f and g is difficult. It could be any nonlinear difficult function. I hope that they're differentiable, because this is my assumption that it's smooth, so I can find derivatives of these functions, but not many other assumptions. So this could be any arbitrary function, practically speaking, which is smooth enough. Okay, so I will substitute, instead of x, I will substitute that expression, so it will be d to dt, which is dot of xe plus delta x, and obviously dot on something constant, and x equilibrium is constant, right? So dot on something constant is 0, so I can ignore that. You'll have delta dot, it's actually dot of the delta x, which is, think about that as single symbol, okay, the 2 letters, all right, equals to f of that thing and that thing. So I'm replacing everywhere x with that expression, which is from here, and u with that expression. So this is x and u, right? Same thing for y. Y plus y equilibrium plus delta y, so a small change from equilibrium point, equals to g of that change plus that change, okay? Haven't got too far, okay, canceled that xe so far. Okay, haven't moved too far. I still have the function f, function g, difficult to work with. So I want to remind you how we deal with linear approximations in general for all functions in calculus. We have Taylor series to handle that. Okay, remember what Taylor series are? It's polynomial approximation for any function. So you can approximate any function around particular given point as just polynomial of particular order, as infinite order polynomial if you want to approximate it precisely. But we will pick only the first order approximation, which means constant part of the Taylor polynomial plus linear part. And this is exactly what that thing is doing. This is practically Taylor polynomial. So if you want, you have some curve, I don't know, let's say this is, I don't know, x squared. No, this, you don't want some polynomial, let's say exponent of t. All right, so this is x is t. You have some exponents that you want to approximate at particular point, 2 or whatever. Right, so t equals to 2. You want to approximate that function around e squared exponent somehow. So you're finding first derivative, second derivative, third derivative, and so on. And you get better and better polynomial approximations for that curve. It comes closer and closer to the curve. But the first approximation is constant, which means what would be that constant in Taylor series that you would expect it to be? It's just value of the function, which will be that approximation, constant. Right, it will be flat line crossing through that point. This will be your Taylor polynomial approximation of the first of the zeros order, right? But this is not great approximation, right, for exponential function, obviously. So you want better approximation. And this approximation will be linear. So you'll take z constant plus first derivative divided by 1 factorial, whatever, and you'll get slope of that line, okay? So here's how it looks like. This is polynomial for the regular functions, one-dimensional functions. So if you want to find what happens to any location close enough to equilibrium point of that function, it's not only equilibrium, it's like any point, practically speaking. You're taking these derivatives, dividing by k factorial, multiplying by polynomial term, which is same x. And pay attention that x here is scalar x. It's not vector x, it's just any scalar. Okay, we call it t here, but doesn't matter. So first two terms will look like that. It will be function of xe. And this will be exactly that green line here, right? Constant in time, plus some function of time, right? And this function of time will be multiplied by the derivative, because your approximation practically looking like that, right? So at that point, you are putting the triangle, right? And z divided by z, this is your derivative, right? At that particular point when all of the segments are super small, super close to that point. It's like you're getting closer and closer and closer until you get that approximation of the derivative, right? So taking all of these points, okay, coming closer, closer, and closer until that ratio is approximated by the derivative, right? And this is how you find the slope of that line. Derivative is practically slope, right? Slope of the linear thing. And this is your first order approximation. Now, you have Taylor series, which you haven't probably learned in calculus courses, which are for multi-dimensional variables. So it works not only for scalar x, but it works for vector x of any kind. More than that, you can write that same thing for multiple functions as a system of functions of Taylor approximations, which means pay attention that in our definition here, f is like f1, f2, f3, depends on the number of equations that you have. So for each x, you have x1 dot, x2 dot, x3 dot. For each one of them, you have like f1, f2, f3. You have multiple f functions. It's a vector of functions, right? And this also could be vector of functions if it is MIMO system, right? So for each one of them, we need to write that approximation. This is what we are doing here. F might be vector of functions, okay? F1, F2, F3, and so on. And X might be a vector of X1, X2, X3, and so on. And X equilibrium 1, X equilibrium 2, X equilibrium 4, whatever, okay? Depends on the size of the system. So it approximately equals to something like that with gradients, Hessians, and other things of that kind, okay? But we are not using all of that part. We ignore all of that part. We're using only the first part. And pay attention that for one-dimensional case, this will be exactly the same. So gradient will become just derivative. Remember what gradient is? It's derivative with respect to the first variable, derivative with respect to the second variable, third variable. This is vector of derivatives, first derivatives of all of the x's. Okay, so it's like d to dx, dx1 to dt, dx2 to dt, and so on. That type of vector. This is a gradient vector. At that point, which means that they are n-dimensional slopes here at that point, equilibrium point. This is what that thing is. You multiply that by vector x, like here, right? And then you have constant function of a constant vector xe. This is how you write multiple variable Taylor series. And this is what we will be using for the development of linearization of that thing, because we have multi-dimensional functions here and multivariable functions as well. Okay, a little bit tricky, but not too difficult. You just need to remember that part. So it's constant f of e plus x transpose times gradient of f. And everything is at the equilibrium point. Any questions so far? So here is what we get. So I'm just copying from the previous page how it looks like the first order approximation for any function I. And index I means like which state is that, right? You'll have multiple f functions. And around that point of equilibrium, which I will call here A, and this will include xe and ue. So this is your equilibrium point, input and state equilibrium. So for that particular point, where that x tilde from the previous slide equals delta x and delta u, and your equilibrium point is xe and ue, all right? I'm just putting that in. So practically I'm taking that equation and writing its linear approximation, right? So I'm writing equation of that line, just n-dimensional plane instead of line. This is how it will look like. So I have that thing, which is at equilibrium point, plus gradient times that vector of deltas, which is that x thing, right? I'm just copying practically that equation here with that definition of the vectors. Now, this is kind of product that we actually can compute, right? And we need to compute it at equilibrium point, because all of these computations are at equilibrium point. So this is what you get. You get fi, which is same thing like here, writing that thing explicitly, which are all of the derivatives of fi with regard to x1, x2, x3, x4, and so on, until you get to d to du, right? Because my last variable is u. So I'm taking all of these derivatives for all of these vectors. I know, difficult, but not too much. And I need to compute these derivatives at the equilibrium point. And this is, I'm just explicitly writing all of the derivatives of x's, not derivatives, the actual states and input, like that. So this is the same vector here, all right? So now, to multiply that thing by that thing, this is just dot product, right? This is that vector by that vector, will give you dot product. So it's sum of element by element multiplication, right? This is what I'm writing here explicitly. So you left with this one, plus delta x1 is this one times this one plus next one times the next one until you get to this one times this one. This is what you get. A long equation. Now, we know that this thing at equilibrium is defined as 0, right? So this part here is just by definition 0, because this f function equals to x dot and x dot equals to 0 at equilibrium point. So this thing cancels. You are left only with these things. But look how they are built. This is very interesting. Because if you think about that part and that part and that part as new x, okay, so these deltas of x are your new x, okay? And these are constants because you compute them at a particular point, right? X equilibrium and u equilibrium are constants. So you compute the derivative value at particular point, which gives you some number, right? It's like slope here at that point for one dimension. But if you have more dimensions, you have multiple slopes at that particular vector point in n-dimensional space. So think about that as just a bunch of numbers. So it's constant times first x plus constant times second x, and so on, plus some constant times u. And this is your first equation. Do you recognize the pattern from linear systems? This is exactly what that thing is. It's like first row in the matrix A multiplied by vector x, and first element of matrix B multiplied by u. This is exactly what that thing is. Okay, for I equals to 1, for example. But then you can repeat the same thing for I equals 2, 3, 4, whatever number of states you have. And you will have each separate line of matrix A be defined by these things. Okay, and B matrix will be defined by these things. This will be the rows of matrix B. That's exactly what that thing is, right? This is linear combination of numbers. So this is exactly what I'm writing here. I'm saying that this function will be approximated by these things, and I will be able to write it as a matrix times vector, new vector, which will consist of delta parts, okay, plus B times delta U. And now I can do the same thing for Y. So for Y, it will be a little bit different because Y equals to G, right? Remember, we defined Y equals to G of X and U. So if I develop Y into YE plus small delta Y, I will have Taylor series of that, which will be that constant, same constant thing, which will be at the same point of equilibrium, plus dg to dx1 and so on, that vector dot product with that vector, which will give you exactly the same linear thing. But what happens to this thing? Okay, why this thing is cancelled? Because Y equilibrium, which is that part, is defined as G equilibrium, right? So the output at equilibrium, because Y equals to G, right? So Y equilibrium equals to G equilibrium by definition. That's what it is. So this part will cancel with this part. And you'll be left exactly with the linear type of equation where delta Y equals all the linear combination of things. Okay, so everything else cancel out. And this is the summary of all the developments that we've done so far, okay? So you can write that matrix as that type of matrix. Do you know the name of that matrix? This is actually a very famous type of matrix where all of the first derivatives, all of the combinations of first derivatives for multivariable and multifunction problems. Jacobian, this is Jacobian of the function f, okay? And you probably even used Jacobian in multidimensional calculus, where you had integrals and you needed to transform system of coordinates with Jacobians. This is exactly that thing. Okay, this is Jacobian matrix, right? Matrix B will be defined df to du because you can see it here, right? These are these things, okay? These elements are B elements for different functions I equals 1, 2, 3, 4, 5 for different functions, f1 through fn. C will be dg to dx, and d will be dg to du all at equilibrium points. So all of them are constants practically. All of this derivatives here will be constants, constant coefficients. But now pay attention that this is not your original system, right? Your original system is x dot, and here is dx dot, delta x dot, right? So it's different system really. So if you want to convert it back to your original system, you will need to do some sort of bias to the equilibrium point of your linear results, because linear system will always converge to zero, for example, if you have zero input, right? But your real nonlinear system will converge to equilibrium point. So if you have particular output which is zero, for example, it will need to become y equilibrium, not zero. So you'll need artificially to shift it to y equilibrium after you compute that convergence. So the dynamics will be linear, right? So dynamically the system will develop by these equations, okay? But around equilibrium point. So you always need kind of to move it to equilibrium point after you have linear solution. So it will be that solution of y, for example, plus equilibrium point. Okay, so you artificially need to add to state equilibrium point, and to y equilibrium point, and to u equilibrium point, because all of the other things will be around that point. Okay? Any questions? I read some deep question in your eyes. Why this guy wants to kill us with calculus? Now, this is not my intent, okay? You'll be fine. You don't have to remember all these books by heart. All right, now we're getting to stability of equilibrium points. How do we know that some point is stable or unstable for nonlinear systems? So here is very simple theorem. Simple, okay. Simple compared to another Lyapunov theorem. So this theorem was developed by Lyapunov in 1800s, somewhere, maybe 1860 or so, long time ago, long before people thought about control systems, and it was practically pure mathematical stuff. He worked on control systems. He was one of the pioneers of state space control in general. And he probably is the reason that Soviet Union went that direction when they developed their theory for controls, which was very different from West, where people in West used only transfer functions and that kind of controls. So his second theorem we will learn next time. It will be much more complex than that. Unfortunately, not too bad. But you will need to invest some time thinking about what it all means. And we'll talk about Lyapunov stability, which is weaker kind of stability than asymptotic stability, for example. But here I'm talking about regular asymptotic stability that you're familiar with, okay? So for asymptotic stability, I think this theorem is actually called second Lyapunov theorem, because the original one is the first one we will learn next time. But this theorem states something like that. Let's say you have some equilibrium point for your nonlinear system. And then you can do linearization, which means the system is differentiable. You have smooth enough differentiable system. You make in linearization, you get a matrix A for that system after linearization, which is a Jacobian matrix, okay, around that particular equilibrium point. How can you know that this equilibrium point is stable or unstable? Which means that trajectories around that point will converge to that point or diverge from that point, go somewhere else to some other attractors. So here's his theorem. It states that if all of the eigenvalues of that matrix, linearized matrix A, are stable, which means real part is less than zero, negative, then this is stable equilibrium point. All right, this is part one. Part two says that if you have at least one of the eigenvalues which is non-stable, then the system, the equilibrium point is unstable, no matter what. So far, it's exactly the same theorem that you used to for regular linear systems, right? LTI systems. But now here's a catch. If you have them less or equal to zero, which means that if you have all of them kind of stable, but you have some which are on the axis, zero, you have eigenvalue of 0 or on j omega axis somewhere, okay? Then we don't really know what happens to the system. Nothing could be said about the system. It could be stable, could be unstable. We have no idea what happens to that system, if it will be stable, if you have something on the j omega axis, all right? So this is a tricky part of that theorem. And you need to remember that for nonlinear systems, you might have 0 eigenvalue. For linear systems, we define that as non-stable, but for nonlinear systems, they still could be stable. It depends. But how would we know if they're stable or unstable? For that, you have the other Lyapunov theory. It's like entire theory, entire lecture on how Lyapunov defined different kinds of stability, different levels of stability, and how we can know. And practically speaking, solving that problem takes like a PhD, all right? So if you want, it's like about Lyapunov functions, how you design Lyapunov function, and people actually got PhD on designing Lyapunov functions for particular plans. It's like state-of-the-art stuff. It's not that easy. You cannot guess it. You need really to develop it, and you have entire theory how you can pick and guess some of these functions, but in most cases, it's extremely difficult to develop function which would tell you if the system will be stable or unstable. That simple question, like what happens if your eigenvalue is 0 or like j or whatever, okay? In that case, this becomes extremely complicated problem. Don't design systems with eigenvalues on the j omega axis, okay? Otherwise, you're in trouble. Any questions? Okay, a few examples for linearization of different systems. And I'm not interested that you will remember all of the physics of like how you develop all of these equations. I'm just giving you the equations, whatever they are. You don't even need to remember what variable names are, what it means. From our mathematical perspective, theoretical perspective, we just need equations. We need to understand what is the nonlinearity in these equations and how we linearize them. And this example is pretty standard example of inverted pendulum on the cart. Okay, many people even do that in the lab, that experiment how to stabilize inverted pendulum. So you have cart which can move left and right, and you can pull some force which we'll call mu, right? So you can pull it back and forth, this particular force, and you have that inverted pendulum which is sitting here and connected here. You want to stabilize it so it will stand like that. So you kind of moving that cart, the thing will stand. Can you guess how many equilibrium points the system has? And will they be stable or unstable? So equilibrium point means that wherever you leave that thing, it will stay there. Don't touch, no disturbances, no nothing. Like put the pendulum at a particular angle or whatever, and it will stay there forever. 2.
That's fine.
So natural thing for that thing will be pendulum just down, right? Just hanging down. This is, will that be stable? Of course it will be stable. No matter how much you move that cart, it will swing a little bit and then it will stabilize at the equilibrium point at the bottom. Okay, so this is natural point for this pendulum to be. But this is not very interesting to control, right? But it will be there anyways. It's more interesting to stabilize it around the upper position of the pendulum, where it will stay if it is exactly 0 angle. If that phi is 0, then it will stay there forever. And no matter where the cart is, right, it will stay, assuming that the surface is flat completely, right? And no disturbances, noise, no nothing, ideally. So this is unstable, but equilibrium point. And this is where we want to linearize and stabilize that system that will be stable and to define force mu in such a way that it will work somehow, okay? Again, you have rod angle, gravitation, linear translation will be called S. So this is where the cart is. And we don't really care where it is. We can linearize around 0, for example, but you can linearize around any other S point because any of the S points will be equilibrium point, technically speaking. and you have other parameters. So pay attention. These are two equations which are describing that, and that L prime is given here with all kind of moment of inertia and other physical coefficients. All of them are numbers. So which of these equations are nonlinear? So I have three equations. Which of them are nonlinear? They're not in state space yet. They're just regular differential, not regular, nonlinear or linear differential equations, or non-differential equations, algebraic equations. So what do you think? Which part here is nonlinear? Remember, linear is just combination of coefficients and x's or variables. And linear differential equation is just like a polynomial, but instead of powers, you have dots. So pay attention to what your variables are. First of all, your input is mu, right? This is u, if you wish, okay? This is input, we call it mu. Your variables are s, is where the card is the state that you will have, and maybe as dots and other things of that kind. And also you have phi, which is the output angle, which you want to be 0. Okay, so these are variables that you have in the system. Practically everything else is constant. So phi is changing, and s is changing, and mu is changing. Mu you're providing, mu, and s is changing, and phi is changing, right? Everything else practically is constant. So in terms of nonlinearity in the variables which are changing, what is nonlinear here? Let's start with the last one. This is easy. Is that nonlinear equation? No, this is just constant. All of it is number. So L prime equals to some number, whatever it is. L is constant, M is constant, J prime is constant. All of them are constants. And all of that is just number. Okay, how about this equation? Is it nonlinear equation, linear equation? Okay, who votes for linear equation? Who votes for nonlinear equation? You cannot stay silent. You need to pick one or another.
Linear.
Okay, so let's vote the other way around. So whoever is not voting now, saying this is non-linear, which means we are voting for linear now. Okay, how about linear? Okay, half and half, interesting. So why do you think this is non-linear? The ones who haven't voted now. Like what part of that is non-linear? Division by m? But 1 divided by m is just number. And f divided by m is number. So you remember how linear equations look like in general? You have y 2 dots plus a times y dot plus by equals something with u, whatever. So it's just constant coefficients of some kind times all kind of derivatives. So this equation is linear. You have just derivatives which are multiplied by constant numbers and inputs also multiplied by constant numbers. Okay, they are not any nonlinear functions of derivatives of some kind. Okay, all right, so this is linear equation. How about this one? This is obviously non-linear equation because your variable sitting inside of the sine and cosine function. All right, so this is why it is not linear, not because of these divisions. All of that is constant, some derivatives which are linearly expressed in the equation. So it's like something multiplied by the derivative, still linear, right? But cosine of phi is not linear and sine phi is not linear at all, right? All right, so, I mean, I have some numbers here to simplify it, but it doesn't matter really. Here is the developments that we are doing. So these are 3 equations that I mentioned in the last page. I will define x1, x2, x3, and x4. Since you have 4 derivatives total, you need system of fourth order, right? So I define x1 as s, x2 as s dot, x3 as that thing, whatever it is, something with s and phi, and x4 is as dots of the previous thing, right? And now you can do some manipulations on the equations to get them in a simpler form. And now you need to write everything as a function of x. You remember our first or second lecture where we had all the definitions. Same thing here. You just need to develop state space equations. You need to compute what x1 dot, x2 dot, x3 dot, and so on. And you need to write everything as a function of x and u. This is how state space equations will look like, okay? So x1 dot, which is s dot, equals just to x2 by definition, right? From that equation. x2 dot equals that thing I'm taking from that equation, because x2 dot is s2 dots, right? And s2 dots is given here, this equation. And this equation is linear, so I'm staying with linear equation. And this will be my u in the future, right? Mu and u are the same thing in that case. x3 dot, again, by definition, equals dot here, so it's x4. And x4 dot, I need to compute it somehow from that equation and from definition here. So x4 dot will be x2 dots plus L prime phi 2 dots. And this looks similar to here, some algebra, and that kind of transformation. After some algebra, you get some nonlinear long expression, okay? You can just check at home that you can actually get to that type of expression to make sure that you know how I've got there. If you have any, and this is potentially one of your future questions, how I've got there. You cannot get to that thing, let me know next time. If you cannot get to that equation from that equation and from that equation, all right? But algebraically, you should get to something like that. As you can see, this is a sign of something pretty complicated, non-linear thing. Everything else is linear, all right? So now we need to compute all of the values, all of the Jacobians and all of the other derivatives of that system. And pay attention that for all of the linear equations, they will be just coefficients that you have in linear equations. That's it. You'll get exactly the same thing. So let's see. We developing the Jacobian matrix. If you remember, this is df1 to dx1. So df1 to dx1, you have no x1, so it's 0. df1 to dx2, you have x2, so coefficient of x2 is 1. You get 1. You do not have x3 and x4, so both of them are zeros. Okay, so far. And pay attention that all of them, if you have linear equations, the coefficients will be like a regular A matrix that you will write from the system of equations. Because the derivatives with regard to particular state number will be coefficients. This is linear, simple. So you have no coefficient of x1. You have that coefficient of x2, no coefficient of x3, no coefficient of x4, right? So it's like 0, 0 here. The third equation, again, 0, 0, 0, 1 coefficient, which multiplies x4. For x4, this becomes tricky, okay? So you need to make derivative with regard to x1, derivative with regard to x2, x3, x4, you have them here, all right? And all of them need to be at the equilibrium point, which is x equals to 0, right? So you're just computing all of these derivatives of that complicated equation. This is why you sometimes need to remember calculus to make derivatives of cosine and sine. And also you have also multiplication, which is a little bit more complex than just sine and cosine. Actually, no, you don't need to remember derivative of multiplication here because you have only multiplication of x2 by something which is not a function of x2. So they are completely separate. For the partial derivatives, this is just constant. Okay, you don't need to remember multiplication rule. All right, so you compute all of the things and you get all kind of coefficients at x equals to 0. So just copying these coefficients here. Okay, all of the derivatives, and you get the A matrix. If you want all of the other matrices, like for Y, you're doing the same thing for derivatives of G, like dg1 to dx1, and so on and so on. You build the vector of C. Same thing with B, you're doing df to du, okay? And your u will be mu. So it will be, practically speaking, 0, 1 divided by m, 0, and it will be here. It will be mu is only here, so it's something divided 1 divided by m multiplied by 1 minus cosine, but this will be 0, right? At equilibrium point. So it will be cosine of 0. Cosine of 0 is 1. 1 minus 1, it will be 0. Okay. So it still will be 0. So you will have mu only here. And coefficient will be 1 divided by m. So it will be 0, 1 divided by m, 0, 0, something like that. I calculated it correctly. All right. Now, stability of that particular point. So we already guessed that this is unstable for obvious reasons, because it will fall down if you are not doing anything with it and moving it a little bit, shaking it a little bit, it will fall down. But you can see that eigenvalues of that matrix are 0, minus 1, minus that square root, and plus that square root. So this is very unstable. It has that thing, which is unstable. All right. Any questions so far? Okay. So let's try another example. You have closed loop system now. And now we're getting kind of closer to controls 1 a little bit. It's nonlinear systems. But you have some non-linearity here, okay? This is practically part of the plant. You have linear part, which is some transfer function, and you have nonlinear part, which looks like that. So it takes that thing cubed minus 27, whatever. All right, so this is just nonlinear parts, and you have linear part, and you have closed loop. What you want to do is to write differential equation, which is describing that entire system. Okay, this is part A. And then you want to define state in particular way and write state equations. And then you want to find equilibrium point for that particular nonlinear system now. And I'm asking you to do that around constant value here of 6. You can pick any other value, but 6 works nicely with computations. Something will cancel out. And then you need to discover if this point is stable, equilibrium point is stable. And then we want linearization matrices A, B, C, and D for that thing. So here's how we solve it, okay? Let's start with the first part where we want to write differential equation for that system. So how do you start in general solving problems of that kind? First of all, you want to write differential equation which connects U and Y. And you know how to do that. This is transfer function, right? So you can write the regular linear differential equation which connects U to Y. Then you connect E to U, and then you connect Y to E. So you have system of multiple potentially nonlinear equations, okay, including differential equations, which you need to combine together in the same equation. Practically, most of it is just algebra, how you solve system of 3 different equations that you will have. But let's write these equations first, okay? So you write down everything you know about the system, and if you remember, if you have some block diagram of any kind, you can connect all of these lines through equations. You can write equation connecting E to R and Y, equation which connects U to E, equation which connects Y to U, and then you have all of the loop connections together, and then you need to manipulate the equations in such a way that you'll get single equation, which means you need to get rid of these parts, practically speaking, these variables which are, you need to keep R, you need to keep Y, which are your input and output, but you want to get rid of everything else in your equation, all of the other variables. This is the direction that we are going, okay? So let's see what we can do here, okay? So Y divided by U, which is that part divided by that part in Laplace domain, will be your transfer function, which is given here, okay? So I'm just writing the transfer function as s squared plus 12s. So from that, you can cross multiply to get differential equation out of it. How you convert transfer function to differential equation, cross multiply, and then doing inverse Laplace transform on both sides. right? Remember one of the first lectures? And this is how you get it. So you're replacing any s multiplication by dot. If you have s squared, it's 2 dots. S multiplied by something is 1 dot. Okay, this is how you get to that equation. So you get s squared y plus 12sy equals 1 times u. You get that equation. From that equation, you get y 2 dots plus 12y, right? Replacing s with dot equals u. And all of them are functions of time, obviously, right? U is function of time and y is function of time. But I want to get rid of that u somehow. So I want to write u as a function of e. And later I will want to get rid of e as well. So u is a function of e, and this is that function of e, which is written here, right? So I'm replacing that with e cubed minus 27. So u equals to fe, and e is equal to r minus y, right? This is the error. It's r minus y, which is coming from here. So this is that additional equation. I'm not writing that explicitly. You can write that explicitly, that e equals to r minus y. Okay, so I'm substituting that e here and getting f of r minus y. Okay, so far? All right. So what is that function? This function is taking whatever is inside the parentheses, cubed minus 27. So I'm taking that r minus 1 cubed minus 27. Okay? Clear? Now I can rewrite the actual equation that I have here. And I will call that equation number 1 and that equation number 2. So u equals to that thing. Now I want to substitute that u here because I want to get rid of u, right? I want to keep r, I want to keep y. I don't want e and I don't want u because they are sitting in the middle here. I want only inputs and outputs in differential equation. So I'm practically putting that part here, okay, and getting that differential equation. Or I can move that r minus y part to the left, that all of the y's will sit on the left and all of the u's will sit on the right. Or I can move all of them to the left. It depends on how you want to write it. So it's fine to keep it like that. And that's fine to keep it like that. I mean, you can do whatever you want. Any questions so far? So this is your differential equation. This one or this one, equivalent. Or you can open that thing and try to move some of the r's to the right. Whatever, it will be complicated because then you will need to solve cubic equation here to get rid of the connections to y. All right, so this is part A. In part B, we want to define state as y and y dot. These are my x1 and x2. And pay attention, this is a second order, so I need only 2 states, right? So as I define them, x1 equals to y, x2 equals to y dot. So x1 dot equals to y dot, which is x2. And x2 dot equals y2 dots. So I'm using that equation, and I'm moving that part to the left, because y2 dots equals to minus that entire thing. And I'm just copying it here, okay? But pay attention that y is defined as x1, so I can replace x1 here, and y dot I can replace with x2. So I'm writing everything as a function of x1 and x2 and r, which is my input. My y by definition will be x1. So here I have non-linear system of state space equations, where x1 dot equals to x2, this is linear, x2 dot equals to something non-linear because you have some cube here, right? And y is still linear, equals to x1 by definition, okay, because this is how I defined it here. Questions on that part? These are my state space equations. Obviously, I cannot write them right now as a matrix because this is non-linear, but this is still state space. All right, so how can you find equilibrium point for r equals to 6? Now you have constant input 6. You want to see what is the equilibrium point of that non-linear system, or maybe multiple equilibrium points. All right, so what we need to define is x1 dot equals to x2 dot equals to 0. This is how you find equilibrium points, right? Which means the function f1 and 2 will be equal to 0, practically speaking. So the first function will be x2. So x2 must be 0 to make it equilibrium. The second function, I'm just reminding you that I'm just copying that thing here. So second function need to be 0. So I need to solve that system of equations. First one I solved, I substitute x2 equals to 0 here, so this thing cancels, okay? And now I have 6 minus x1 cubed minus 27 equals 0. Okay, this is equations that I need to solve. And for that case, x1 equals to 3, which means that your equilibrium point is 0, 3. The second one will be 0, the first one will be 3. This is your equilibrium point for x. And our equilibrium will be as given 6. Right? Okay, so far? So last thing that we need to do is to find all of these derivatives, Jacobians and other things like that. So we're just finding df1 to dx1, df2 to dx2, df1 to dx2, all of the combinations for these functions, okay? So you compute them and you get these two functions. You compute derivative with regard to 0, to x1 is 0, with regard to x2 is 1, with regard to this thing. Okay, if you make derivative with regard to x1, you get that derivative, which means this thing false, obviously, because it's not a function of x1. The only thing which is related to x2 here is negative 12, so you have that negative 12 coefficient here. And when you substitute x equilibrium and r equilibrium, instead of r and x1, you get that matrix. Okay, same thing with b, but you are doing derivatives with regard to r, which is your input. Okay, so this is not a function of r, so it's 0. This is function of r, so it's 3 times that thing. Okay, at x1 equals to 3. So you'll get that value 27, and so on. Same thing with c, you just substituting that two formulas. And if you want to check stability, you're just looking for eigenvalues of that matrix, which are -3 and -9, which means this equilibrium point is stable. Okay, and done with that exercise. Any questions? All right, thank you.